All right, so chapter 11 is all about making predictions. And today we have a nice little lesson about predicting a winning percentage. So having a calculator is going to be very important. This lesson does not need a graphing calculator, but please go get a calculator right now. So if you need to pause so that people get calculators, that would be great. Okay. So in this chapter, we will learn how to use relationships between variables to make predictions and seek explanations. We will start by exploring what it takes to build a better baseball team. The ultimate goal of every team is to win games. Some teams win more games than others, and since scoring more runs than your opponent is the key to winning games, it makes sense to investigate the relationship between runs scored, so runs that your team scores, runs allowed, runs the other team scores against you, and winning percentage. So Bill James, one of the original and most famous sabermetricians, who are people that use statistical methods to analyze baseball, proposed what is called the Pythagorean expectation of winning percentage. This is James's formula. RS here is going to represent runs scored, and RA will represent runs allowed. And so the predicted winning percentage is RS squared over RS squared plus RA squared. And I want you guys to put that denominator in parentheses. That's really important when you enter that in the calculator. Because if you just enter in the calculator this without parentheses, this always cancels to make 1, and then it's a hot mess, okay? So make sure you put the denominator in parentheses when you put that in the calculator, okay? And they call this particular formula the Pythagorean just because it involves squares. And you know the Pythagorean theorem involves a squared plus b squared equals c squared. So example 1 says, consider the statistics for the 2008 Detroit Tigers, who scored 821 runs and allowed 857 runs. Well, let's calculate the Pythagorean predicted winning percentage. So for our predicted winning percentage, which I often abbreviate PWP, note we take the runs scored squared, so that would be 821 squared. And in our denominator, I'm going to open the parentheses. There's runs scored squared, so 821 squared plus runs allowed squared, so 857 squared. And then we can just put that in the calculator and calculate. So 821 squared divided by, open parentheses, 821 squared plus 857 squared. And I like to close the parentheses also, just for good measure. Okay, so that's what it should look like. And we end up getting, we like to round to 3 decimal places here to the nearest 1/10 of a percent. And so if I look, that 5 tells me to bump that 8 up to 9. Please round appropriately. When you don't round appropriately at first, it throws everything else off. You have to follow rounding rules. So if we're rounding to the nearest 1,000th, that tells us that we're going to have 0.479 approximately. So this is about 0.479. So that means that that would be about 47.9%. So with that information, we are predicting that the Tigers win 47.9% of their games. Now let's find the predicted number of wins, knowing that they play a 162-game season. Well, here's how you would do that. The predicted number of wins, you're going to take your predicted winning percentage, in decimal form of course, and then multiply it by the total number of games. Okay? So what we'll do then is we'll take our predicted winning percentage as a decimal, 0.479, and we'll multiply it by the total number of games that they played, 162, and that will tell us about how many games they won. So if I do that, so I'll take times 162, and I get 77.598. So 77.598, okay? Now, there are two schools of thought here. I understand that, well, you can't win 0.598 of a game. I understand that you haven't yet won that 78th game, but there are some of us that still don't know how to round. So I would like us to practice those traditional rounding rules for these cases. I do want to make you guys aware that sometimes they do quote-unquote round down because that win hasn't happened, but I do want us just to practice regular rounding rules. That being said, you can't win a fraction of a game, so this has to be a whole number. That 5 tells us to round 77 up to 78, so we expect them to win 78 games. Now, in 2008, the Tigers actually won 74 games. How does that compare to our prediction? Well, our prediction was 78. They actually won 74. So we can see that the prediction was off by 4 games. Now, how do we decide whether we say positive or negative? Well, that's what we're going to define here. This difference between the actual number of wins and the predicted number of wins is called a residual. The residual is the actual value minus our predicted value. Okay? So we always take actual minus predicted. If you switch it, it's wrong. It's going to be opposite of what it's supposed to be. Think alphabetical. A before P. Actual minus predicted. Okay? When a residual is positive, that means that the actual value was greater than the predicted value, so our prediction was too low. And when a residual is negative, the actual value is below the predicted value, so the prediction was too high. So let's calculate the residual for the 2008 Detroit Tigers. Remember, we're going to take the actual value, which was 74, minus the predicted value, which we had as 78. And so our residual is -4. So that's our residual. And if it asks us to interpret the residual, we want to talk about what this means. So because the residual is negative, we can say that the Detroit Tigers performed below their prediction. And this was talking about winning games. So that means that they won 4 fewer games than expected. Okay? And sabermetricians often attribute these residuals to luck, or in statistical terms, random chance. So it could be random chance that is the reason for these residuals. Some people argue that the ability to win close games help explain the size of residuals, but in a sense, we can say that these residuals could be random chance. By the way, what do you think the ideal residual would be? Remember, our goal is to make accurate predictions. So our ideal residual would be if our prediction was spot on, right? So what would that make the residual? Well, that would make it 0. So let's just keep in mind as we go through this chapter that our ideal residual is going to be 0. That would mean that the actual value and the predicted value were exactly the same. Okay? So now that you've had a chance to do that, I'd like you to pause and try this question. So you're going to look at a different 2008 team, the Phillies, and you're going to find their Pythagorean winning percentage, their predicted number of wins, and then you'll find the residual and interpret the residual. This is what finding the residual looks like. This is what interpreting the residual looks like. So please pause and take a minute and do the you try on the back. Okay, so let's take a look at what you guys had. For the predicted winning percentage, You take 799 squared over 799 squared plus 680 squared. It gives you 0.57999. You do not chop it off. You round that to 0.580 or 58.0%. To find the predicted number of wins, we take that winning percentage, 0.580, multiply it by 162 games, and then we get 94 games. To find the residual, remember it said that they actually won 92 games. We predicted 94 games, so that's a residual of -2, meaning that the Phillies performed below their prediction. They won 2 fewer games than expected. So that's the gist of most of the homework tonight. But I want to start talking to you about some other pieces here. Why did Bill James choose 2 as the exponent? So there's actually a more general formula for predicted winning percentage that still uses runs scored and runs allowed. Instead of knowing what the exponent is, we could just have an x as the exponent. And then what we could do basically, so rs to the x over rs to the x plus ra to the x. And then what you could do is you could try different exponents and see which one works best. Remember, the ideal residual is 0, so the best exponent is going to be the one that is closest to 0. So let's pretend that we didn't like using 2 as an exponent, and someone said we should use 1 as an exponent instead. Let's recalculate the predicted winning percentage using x equals 1. So in this case, the predicted winning percentage would be 821 to the first power over 821 to the first plus 857 to the first. Okay. And I know that to the first doesn't change it, but in case, just put the exponent there. Okay, so we're going to take 821 divided by 821 plus 857, okay? And that's going to give us 0.489. Or 48.9%. So that would be the predicted winning percentage using x equals 1. So now, with this predicting winning percentage, how many games do we predict that they win? Well, again, we take the predicted winning percentage as a decimal, 0.489 times 162. And we'll just round that to 79 games. Okay, so now we're predicting them to win 79 games. Let's find and interpret this residual. Remember, they actually won 74 games. So remember, our residual, we're going to take our actual, which is 74, minus our prediction, which is 79, and that gives us a residual of -5. So to interpret, we can say that the Tigers, in this case, performed below their prediction. Again, because it was negative, that means that they won 5 fewer games than expected. So that would be our interpretation of that residual. So now we come to the question, which exponent, x equals 2 or x equals 1, appears to be better and why? Well, let's recall what happened when x was 2. When x was 2, our residual was -4. And when x equals 1, our residual was -5. So which one is better? Remember, the ideal residual is 0. So which is closer to 0? This guy right here. Now it's asking which exponent appears to be better. So the exponent that's better is x equals 2. So we'll articulate that in our answer. X equals 2 is the better exponent because the residual is closer to 0. And that's really key here. The idea of being closer to 0 in a residual sense is always a better prediction. Okay? And you could choose lots of different exponents also. You could try 2.1, 2.2, 1.8, whatever, but just for our purposes for comparison, we just use the whole numbers. Okay? Now, the thing is that we just looked at the Tigers. To decide if an exponent of 2 is really the better exponent, we have to look at the residuals for all teams, not just the Tigers, to compare the predictions with these two different exponents. And so this sum of squared residuals, which is the SSR, is one way to measure how well a model makes predictions. The SSR first starts by finding the residual, so leave a little space. Remember, the residual is the actual minus the predicted. So to find the sum of squared residuals, you start by finding the residual. The issue is that we're going to be adding them up, and so if we add positives and negatives, it is going to balance out to be close to 0. So what we want to do is to give each one weight. To give positive and negative residuals equivalent weight, we're going to square it. That way, a negative 4 would turn into 16. A positive 4 would also turn into 16 because they have the same distance from 0 that way. And then we're going to use the sum symbol that hopefully you saw in Algebra 2. That's uppercase sigma. And that's how we would calculate the sum of squared residuals. Now, the good news is I'm never going to ask y'all to calculate it. But again, I think it's important that you understand what it is that is happening when we're talking about the sum of squared residuals. And so that's what the sum of squared residuals is. Again, if a model makes good predictions, the difference between actual and predicted values will be close to 0, resulting in a small sum of squared residuals. So because you're squaring it, we're not going to see any negative values when we have SSRs. So we can always pick the smallest one when it's an SSR. So residuals, you have to say close to 0. SSR, you are allowed to say smaller. If you want to say close to 0, that's okay too. So with an exponent of 2, they found the SSR for all the teams in 2008. And they found that that was 529. So x equals 2 gave us an SSR of 529. So that means if you added up, if you took the residuals, squared them, and added them all up, you would get 529 with an exponent of 2. With an exponent of 1, the SSR for all teams was 1,215. Which exponent is better and why? And again, here we can see that this was indicates much closer to the predictions because our SSR was smaller. So we can say that an exponent of 2 is better because it gave us a smaller SSR. And again, a smaller SSR indicates that your predictions were closer to the actual values. And that's the gist. So just a lot of computing today. Don't forget your parentheses. We will look at equations for predictions in the next lesson. Have a good one.